Okay, so let's continue our discussion on the Bootstrap following our Monday lecture. So on Monday, we said that for the use statistic, so you can consider this to be the generalization of unbiased estimators. So what this use statistics does is that we define it based on just a kernel function, which we call the G function. And here's the estimator, denoted as theta n hat as for estimator and for the sample size. And UN is for the use statistic. So following our standard definition with two arguments in the G function, and of course, here the setup is that we have an IID sample from some distribution F. Okay, so with this definition, what we are interested in, the performance measure, we denoted by lambda and F. Here we define it as the variance of root n. So this is under our standard asymptotic setting. When we multiply the estimator by root n, right, and then we often have a subtraction of the theta, we have this convergent to an asymptotic distribution whose variance doesn't depend on n. So that's why we multiply n here. And with this, so what we know is that from our previous lecture, we have this variance formula for the U statistic under this distribution F of UN. And I'm just going to write the final form, which we did last time. Okay, and in this form, from our previous lectures, based on that H projection, we can have this sigma 1 squared as the variance of G1 xi. But we also know that it can be written as the covariance of x1, x2, and gx1, x3, meaning that they share one random variable, but the other is different. And sigma 2 squared is just, and also this is under F, it's just the variance of gx1, x2. Okay, so that's our definition. Okay, so now let's take a look at the limit. So based on this, right, and also based on the fact that this lambda NF is equal to the variance of root n times sigma n hat. So therefore, we know it's equal to n times the variance f of un, which is what we have here. So therefore, you can see that lambda NF with this multiplication by n, we can have it convergent as n goes to infinity to 4 times sigma 1 squared. Okay, and this is what we define as the limit of lambda NF, and we give it the notation which we used last time, lambda f. So n is gone. Okay, so this is the performance measure we are interested in estimating using Bootstrap. So what does Bootstrap give us? As we said, we are going to replace F by F and hat, the empirical CDF. Okay, and maybe I need one more step so that it's clear. Okay, so maybe just give me here. So let me just write here. So this will give me lambda NF equals to 4 times n minus 2, n minus 1, sigma 1 squared plus 2 over n minus 1 sigma 2 squared. So I have this. And now I'm going to get a bootstrap version of this. So clearly, you see, n is the same n because my bootstrap sample also has size n. But I'm going to replace the parameters here by the corresponding parameters from my fn hat. Okay, so I'm going to denote it as sigma 1 star square, okay, plus 2 over n minus 1 sigma 2 star square. And then what is sigma 1 star square? What is sigma 2 star square? So correspondingly, we have sigma 1 star square as the covariance now under fn hat, under the empirical distribution given my sample of gx1 star. This is a sample from my empirical CDF, x2 star, gx1 star, x3 star, okay? This is the sigma 1 star square. And then sigma 2 star square correspondingly would be the variance under fn hat of gx1 star, x2 star. Okay, so that's it. See if I can do better with this. Okay, so now given those, and then how can we compute this, by the way? So these two things are theoretically computable. These two things are theoretically computable given my sample. Okay, so let's take a look at here. This means that we are going to sample 3 random variables from x1 to xn. So x1 star, x2 star, x3 star are IID from fn hat. And fn hat is defined based on x1 to xn. So therefore, you can see that this sigma 1 star, if I continue to write it, right, it should be the expectation under fn hat of the product of those two. Let me just continue writing. Times gx1 star, x3 star. Okay, expectation of the product minus the product of the expectation. Okay, right, by definition, this is it. And then what is this exactly? If I continue to write, then you see this expectation is basically the average over the x1 to xn. Each of the xi has probability 1 over n. So therefore, you can clearly see that the first term, I'll just continue writing here, can be simplified as 1 over n cubic. Okay, and I have I from 1 to n, j from 1 to n, k from 1 to n. And what I have is g xi xj times g xi xk. So you see, this is by definition. The reason is that x1 star, x2 star, x3 star can each take x1 to xn with probability 1 over n. So that's why we multiply them. That's the average I get. Okay, and then right here, I would have 1 over n square I from 1 to n, j from 1 to n, g, xi, xj. Okay, this is the first term. And the second term obviously is equal to the first term. So I just square it. So you see how I was able to compute this, because we said that the bootstrap thing theoretically should be computable. But in fact, when n is large, this could be computation intensive. So which is actually fine in our case, but it will get harder and harder later. So that's why we usually approximate this by drawing capital B samples from f and hat and then do Monte Carlo approximation. But here we are doing the exact calculation, okay? And similarly, you should be able to derive this based on x1 to xn yourself. So I'm going to leave that to you. All right, so given those two things, then the question is, by putting sigma 1 star square and sigma 2 star square into this formula, do they converge to the same limit, right? In last lecture, we said that these two things are equivalent. So recall, if we have lambda n f convergent to lambda f, okay? This is equivalent to these two things. We have lambda n f n hat minus lambda n f convergent improbability to 0 and lambda n f n hat. Sorry, I should say, my bad. Okay, I need to swap those two things. Okay, so under this, I should say this way. So if I have this limit, then lambda n f n hat minus lambda n f convergent probability to 0 is equivalent to lambda n f n hat converges in probability to lambda. Okay, so with this is our interest, right? Because this will tell me, if this holds, it will tell me that lambda n f n hat is a good estimator of lambda n f, which is our interest. This is what we're interested in. So therefore, for now, we already have the condition. Lambda NF converges to a limit as n goes to infinity. This is our limit. So then the final question is, does my lambda NF and hat converge to the same limit in probability? That's something we need to get to the good result. Okay. So as you can see, what we have here is this, right? So basically, in order to do the convergence, we need two things. We will need sigma 1 star square converges in probability to sigma 1 square. We also need sigma 2 star square converges or has a finite, is bounded in probability, right? Because this term is going down to 0. So if this is finite, then we're good. So we need those two things. And do we have it? Actually, we need something else to show that. So basically, it is sufficient, I should say, to show sigma 1 star, this thing converges in probability to sigma 1 square. And sigma 2 star square converges in probability to sigma 2 squared. If we have those two things, then we should be fine. So we can have that this lambda n f n hat will convergent limit to converges to 4 times sigma 1 squared in probability. But do we? So given this form, we can take a look together. So one thing you see is different, right? Comparing these two. So this and this, if you compare those two lines, you can see that here when we define the covariance, x1, x2, and x3, they are IID. But in our sigma 1 star square here, we have that issue with the V statistic. That is, here the xi, xj, and xk may have repeats. They may pick the same thing. So therefore, it's not necessarily the case that the sigma 1 star square is convergent to sigma 1 square. But we could actually fix it. In other words, if we have, this is possible, okay? This, which is possible if we have this thing, variance of g xi xi. Okay, this is to handle the repeats here. If we have this thing finite, then we are good. The reason is that, how many cases will we have repeats? Let's look at here. We only have n possible repeats, right? So x1, x1, x2, x2, and xn, xn. So compared to this, if this term is finite, it will go down to 0. So it will not matter to us. So, but if this is not finite, then we cannot show sigma 1 star squared converges to sigma 1 squared. So the take-home message for this derivation is that it shows one example when you want to show that the bootstrap estimate is a good estimator of the performance measure, right? If you want to show this is estimates as well, then what conditions do you need to show it works? So in this case, we can see that, or I should say not possible, this is too loose. I should say which holds. So this gives you a condition. With this condition, we can show this, and that will give me the bootstrap good performance I need. So in other words, we can generally say that under very reasonable conditions, we have bootstrap working for the U statistic. And the key is because the U statistic is some sort of average. And here, when we had the average under the empirical CDF or expectation under the empirical CDF, this is what we get. And although compared to the quantity we want to estimate, like the sigma 1 square, the bootstrap version will involve repeats. But if those repeats are not dominating the term as n goes to infinity, then we're okay. Okay, do we have questions about this part? It's just to show that here bootstrap would work under a very reasonable condition. Okay, so this is a positive example. So as I said in my last lecture, now I'm going to show you a negative example for which bootstrap doesn't work. And that's the case when the estimator or when the parameter we want to estimate involves some boundary of the support of a distribution. In other words, the parameter is not an expectation functional of the distribution. So this is a counterexample. And this involves what we learned before, the extreme order statistic. Okay, so now let's say that, again, IID from distribution denoted by F. And here I just say that F is the CDF of this uniform distribution 0 to theta. So theta is the parameter of interest here. We write theta as TF. So we're getting the maximum or the upper bound of the support of the F. Okay, and then what's the natural estimator? If I do plugging, and here F and hat is defined as a discrete distribution of x1 to xn, right? Then the maximum would be the extreme order statistic. That should be it. Okay, so now let's say that we are interested in this particular performance measure. The probability under F. Okay, let's say that we fix A as non-negative. And now you recall, this is something we have seen. The reason we are interested in this quantity, this random variable, is because from our previous lecture, we know it converges to a good asymptotic distribution, right? The actual boundary minus the maximum times n. What does it converge to? Previously, if you recall, we talked about when theta equals 1, when it's uniform 0 to 1. Here it's n times 1 minus the maximum. And recall that it converges to exponential 1, right? So here we have theta. So therefore, you can consider everything is scaled by theta times multiplied by theta. So therefore, by previous lectures, we have n times converges in law to here, because everything's scaled, theta times z, let's say, where z follows exponential 1. Okay, that's from our previous lecture. So given that, then we can easily say that, right, because this is the limit and this is the CDF. We know that convergence in law implies convergence in CDF. So lambda and F, by this definition, should converge to the CDF of z times theta. Okay, and this is equal to z less or equal than a over theta. Then by the CDF of exponential 1, this is 1 over exponential to the negative a over theta. Okay, so we have the limit. And this limit, by our notation, is denoted by lambda f. Okay, so now let's consider Bootstrap. For Bootstrap, again, we're going to do plugging. Okay, and then you see everything will be changed from F to F and hat. Now the upper bound should be the upper bound of F and hat. So that's xn. Okay, and then this will be the maximum of a Bootstrap sample, and I denote it as xn star, less or equal than a. All right. How can we compute this distribution, this probability? So now one thing we can consider is that, of course, because the hypothetical sample is from x1 to xn, so there's no possibility that this xn star is greater than xn. That couldn't happen. But what could happen is that this thing could be equal to it. Okay, so let's try to do the calculation and see what is the probability that these two things are equal. And also we know that when this is equal to 0, is contained in this event, less or equal than a non-negative A. So therefore, this probability is greater or equal than the probability that they are equal. Okay, we have this. And what is this probability? Let's do a calculation. So when the maximum, when xn star picks xn, it's equal to 1 minus the probability. Okay, let me just continue writing instead of saying. That will be clear. Okay, so this is equal to, under this distribution, okay, so it means that in the hypothetical sample, x1, I should say, at least one of x1 star to xn star takes xn. Okay, it's this probability. And then we know it's equal to 1 minus the probability that none of x1 star to xn star takes xn. It's equal to that. Okay, when none of them takes this, it means that they can only pick from x1 to xn other than the maximum. Okay, so then that probability is 1, I know it's minus 1 over n. So we're just assuming for simplicity that x1 to xn are all distinct, and which is reasonable because they're IID from F, and this is a continuous distribution. So it's reasonable to assume they're all distinct. Okay, raised to the power n, because they all pick other things with probability 1 minus 1 over n. Okay, so now what's the limit of this? We know this, right? This will converge in probability, this will converge as n goes to infinity to 1 minus e to the negative 1. All right, now we can see that we have something that's not really the same. So you see basically with this and with this. So, and given that you don't actually know theta, and this is a lower bound, by the way. This is a lower bound. So then you will see that what I would have is lambda m f n hat, okay, minus lambda n f would be greater or equal than, maybe I should say this, the limit, okay, let me just write it here. The limit of these two things will be greater or equal than this minus, okay. And we know that for some A, this thing could be positive, right? For certain A. And therefore, it has a lower bound different from 0. So we can conclude that in those cases, the bootstrap is not a good estimator for this performance measure. Does that make sense? Okay, so you see, this is the case where when the parameter of interest is a boundary, we have an issue with bootstrap. So intuitively, how do we make sense of this result? The reason is that, you see, given your sample, your maximum is fixed at this, right? So no matter how you draw your bootstrap sample, you can never get a value beyond this. And we know this is not equal to theta. So therefore, there's always a gap. And this is very different from when we talk about average. Because when we talk about average, you are essentially using all your observations in the sample to calculate average. But when we talk about the boundary, essentially only the maximum, that single observation would matter. So I hope this makes sense to everybody. Okay, yeah, so now speaking of that, let's come back to talking about the simple case, average or mean. Okay, so this is a very important result regarding the bootstrap theory, and this is called the bootstrap theorem. So by the name, you can know its importance. And it's about the mean. Okay, so let's say that we have x1 to xn, again, IID, from F with mean, mu, and variance, sigma squared. Okay, so in this case, clearly the estimator, mu n hat, is the average, right? We call this xn bar previously. Okay, so now the performance measure regarding this we're interested in is its distribution. So we call this GNT. It's a CDF function, and it is actually our performance measure. And we define it as the probability under F of root n mu n hat minus mu less or equal than t. This is our interest. We're interested in this distribution, right? This is actually the problem in our central limit theorem. We are trying to talk about the limit of this, and we have the result already. Okay, bootstrap. Now let's say, it's a hypothetical sample. Let's define mu n hat star as xi star. Okay, and we denote this by xm bar star. So then we define this distribution's bootstrap version. We call that Gn hat t. Okay, and it's the lambda n at empirical CDF f n hat. It's the probability under f n hat of the corresponding root n times mu n hat star. That's this minus mu n hat, because that's the mean on my f n hat. Okay, now we want to talk about the relationship between this, and that's the result of the bootstrap theorem. So the theorem says if we have a finite third centered moment for F, we call that mu3. If this mu3 defined as the expectation under F of xi minus mu absolute value cubed, if we have this finite, then we would have the soup of these two functions absolute differences. And this is over T, okay? The soup of those two CDF functions is going down to 0 in probability with the rate 1 over root n. So that's what we write big OP 1 over root n. Okay, this is the Bootstrap theorem result. So what it shows that indeed these two things, right, by our nice property over there, we have their difference for any t going down to 0 in probability. Beyond that, we also have the rate, and the rate is 1 over root n. Okay, so now I think everybody should have a rough sense about how to prove this result, given what we have. So from central limit theorem, we actually know the limit of this for any given t, right? Because we know it should converge to the CDF of some normal distribution at t. And also by the central limit theorem, we should know that this should also converge to some normal distribution at CDF of normal distribution at t. But these two normal distribution cannot be the same normal distribution because this is f and this is f and hat. So that's the rough idea we have for doing this proof. Okay, so now let's quickly review one thing we briefly mentioned, but we didn't spend much time on before. So in order to prove this, we actually need the soup difference between this CDF and the normal CDF. And we mentioned this result as the berry-esseen theorem. Okay, so what this says, this is actually about this result, if you recall. So I'm just going to stick with the notation here. So it's basically saying that if I have the soup, okay, of two functions differences, one is the probability under f, of course, of this thing. Let me see. Yep, root n times mu n hat minus mu divided by sigma, the true variance, less or equal than z, minus the standard normal CDF phi at z, their absolute differences, and I take the soup over z. Berry-esseen get an upper bound for this. So it says it's less or equal than some constant c times the third center moment, mu3, divided by sigma cubic divided by root n. Okay, so what's the key result from berry-esseen? It's actually about this soup difference goes down to 0 on the rate at the rate 1 over root n. So that's something very aligned with what we have here. Except that here there's no randomness involved because this is a fixed probability. This is fixed, right? There's no random variable. So that's why we can say this and this, their difference goes down to 0 as big O 1 over root n instead of big OP. Right, so seeing this, we should have the starting point for doing this Bootstrap theorem's proof. Okay, so from here, let's define some notations. Okay, so the first thing I will define as this, I call this phi sigma. I will define this as the CDF of normal with mean 0 variance sigma square. I'll introduce this notation. And correspondingly, you see, what is the estimator for, or not estimator, sigma square is the variance under f of xi, right? Then what's the corresponding variance under fn hat of x1 star of a hypothetical random variable? I call that sigma hat n square. And what's the definition of that? Based on the definition of fn star, the empirical CDF, this should be equal to 1 over n, the probability mass at each value. Right? This should be it. Because this is the expectation of fn hat. And I'm having each value xi with probability 1 over n. And this is the exact definition of variance on this discrete distribution fn hat. Okay, so using this, I'm going to introduce a notation. This is going to be the CDF of this normal distribution. And you should be able to see that because we consider the sample x1 to xn to be random. So fn hat is random, sigma n hat is random. So this is a random. So there are two layers of randomness. One is the distribution, one is the variance parameter. And therefore, this CDF is a random function, while this is a fixed function. Okay, so with those notations, the next thing we are going to do is to, because this is our target, right, to prove this, we are going to use the triangle inequality to get an upper bound of this by introducing those two CDFs. Okay, so sup g n t minus g n hat t, I'm going to decompose it into 3 terms. Maybe I just write here, sup t g n t minus phi sigma t. That's the first term. The second term is phi sigma t minus phi sigma n hat t. And the last term is g n hat t minus phi sigma n hat t. Okay, I will have those 3 terms. And what I need to show is that all the 3 terms are actually going down to 0 at the rate either O or OP 1 over root n. And being O or OP depending on whether the term is fixed or random. So clearly the first term is fixed, but this is random and this is random. Okay, so I'm just going to be quick. So because I think from here, the derivation is just based on the berry-esseen mostly. So the first term, let me call this A, B, and C. So by berry-esseen, which is a direct application of it, so we can show that one thing we can show is A will be less or equal than C, the same thing, times mu3 over sigma 3 root n. We have this for A, direct application of berry-esseen. And C, by same argument, mu3, but we need to replace it by hat, because in the C term, everything is about the F n hat instead of F. So I call that mu3 hat sigma n hat cube root n. This is C. Okay, how about B? Okay, so for B, it's just between two normal CDFs. One has variance or standard deviation sigma. One has standard deviation sigma and hat. Okay, so we can still show it. The reason is because if I move to here, let me erase the berry-esseen. Okay. So we can show that because when we have the, the sigma n hat square is actually a function of moments. And previously we had talked about the asymptotics of the function of moments. So therefore, if you recall, we could show that the root n sigma n hat square, right, minus sigma square, we could show that this converges to some normal distribution. Okay, so with this result, so what does this mean? It means that when we multiply this difference by root n, it doesn't go down to 0, but it goes to a distribution. So this is equivalent to write this way. Sigma n hat square minus sigma square is actually big OP 1 over root n. Okay, so what does this imply? If you multiply root n to the left-hand side, it's just this term, it's big OP1. So it means that it's not, okay, so we should say that based on the first lecture, if you recall, based on the definition of big OP, it means that it's actually random, but it's actually on the order of 1 or less than that. So less or equal than 1 stochastically. That's what it means. So these two things, so with this asymptotic, what we can have is here. So this result is the foundation of our next result for B. So then coming back to here, you can see that this is a CDF and this is a CDF. So what we can do is that if we do a Taylor expansion for those two functions around sigma, so we can actually, or around sigma square, we can actually write the first term just as the difference. And also we can show that for this dominant term, because it goes down to 0 at this rate, so we can show that the B is also controlled by this rate. So from this, we will get B is less or equal than OP 1 over root n. Actually, I should write equal. Sorry. Yeah, OP 1 over root n. So the three things together, A, B, and C, both are controlled by under OP 1 over root n. And also one thing I didn't finish is that here in the upper bound of C, we have random mu3 hat and sigma n hat. And for those two things, we need some arguments here. Strong law of large numbers. So we're going to show that because mu3 hat is going in probability to mu3, and this is converging in probability to sigma cubed. So therefore, these two things will converge to constants, and we have this rate root n over here. So just to give you a graphical summary of what we have, I think this is very helpful. So we have by berry-esseen the function gn, which is the distribution CDF of this distribution we're interested in. This and its distance from the normal distribution. This is determined by big O 1 over root n. This is by berry-esseen. We have this. Okay, and also from this normal CDF to this normal CDF, we have them controlled by big OP, 1 over root n. The reason is because of the asymptotics of root hat, sigma n hat, and sigma. So that is controlled by big OP 1 over root n because of the asymptotics. Okay, and then finally from here to here, G n hat. We have big OP 1 over root n. This is again berry-esseen. So the Bootstrap theorem is about their distance, Gn and Gn hat. This is what we just showed. Because of this relation, this is still big OP 1 over root n. Okay, and this is the theoretical Bootstrap without Monte Carlo. If we do Monte Carlo, you know what we will do is that we will draw capital B random sample from x1 to xn with repeats, right? So we call that x1i star to xbi star, and I goes from 1 to n. So for that, we would denote it the Monte Carlo version, G, B, n star. It means that it's the average of capital B Bootstrap samples. So in other words, what we will do is for each Bootstrap sample, we are going to compute whether this holds as an indicator 0 or 1, and we will take the average over the capital B. So that will be my GBN star. So let me just write it for clarity. So GBN star, based on our previous notation, this lambda BN star, the Monte Carlo version, and it will be 1 over B summation B from 1 to capital B, indicator whether root n times mu B n hat star on the B's Bootstrap sample, that estimator minus mu n hat. Okay, this will be the Monte Carlo version in practice. So you see, comparing this to this, what is their distance? This is very similar to the distance between this and this, right? This is on the sample version, capital B samples, and this is the expectation. So we know that this is, again, by the asymptotics. We know that this is by big OP 1 over root capital B. And so therefore, you see now the picture is clear. Again, just to echo what we said in the previous lecture, Bootstrap is the practical Bootstrap is 2-step. This is the theoretical one. This is the Monte Carlo one. So the best we can do is to use a very large B to make this very, very small. So it's negligible. Then we are left with this gap. But this gap, you know, for this classical context, when the parameter is the population mean and the estimator is a sample mean, we're good. We know this is going down to 0 at the rate of 1 over root n. So everything is connected. But in the previous counter example, we don't have this gap going down to 0. It could be that this is a non-zero gap, no matter how large n is, then that's an issue. So that's the case when Bootstrap fails. So in other words, whether Bootstrap works or not, it's really depending on these two things, or more generally, the lambda NF and lambda NF hat, whether their difference is going down to 0 in probability. Okay, so this is it. Any questions? The Bootstrap theorem. Okay, so finally, I'm going to talk about a very interesting comparison. So when we do plugin versus when we do Bootstrap, for estimating the same parameter. Okay. So this will be our last topic. So will be the classical plugin versus Bootstrap. Okay, so there are two estimators for the same parameter. So to be more concrete, or maybe let me just be more general. So I will write this as lambda f n hat. I will write this as lambda n f n hat. So what's the difference? Recall that the parameter of interest is lambda n f. This is the parameter of interest. So one way to estimate this, and we know that this, as n goes to infinity, converges to lambda f. So therefore, one way to estimate this is to directly plug in the limit by replacing f by f n hat. This is what we call classical. The other way is to work on this parameter, this finite sample parameter directly, and just this. Okay. All right, or maybe more accurate, I should say, the performance. We are more consistent with the language we used in previous lecture. So lambda NF is always about some estimator's performance. Now we are going to estimate the performance. So here, the classical plugin is an estimator of the performance, and the Bootstrap gives another estimator of the performance. So which of them do better? That's the question we want to answer here. All right, so let's take a look at one example. Let's say that we have IIDF. Okay, and the parameter of our interest we call Tn. Now we should be familiar with this language. The functional of f, we call it the sigma square. Okay, that's the variance. We are interested in this. And we give it a notation here for this example specifically. We call it mu2, the second centered moment. Okay, so now let's take a look at what we call the plugin or the parameter. This one to estimate it. So now based on our sample, right? The empirical CDF of the sample. Again, the variance definition, we've seen this just now. It's 1 over n xi minus xn bar squared. Okay, and following this mu2, we give it a notation capital M2. So when we say capital M, it's a sample-based thing, and the mu is the population-based thing. So mu based on F, M based on F and hat. Okay, so next, we were interested in the performance of this estimator. So the performance we're interested in, called lambda and F, is actually the variance under F of root n M2. Okay, still scale by root n to have a stable asymptotics. Or here, not even asymptotics, not yet. We carry n with us. So let me just write this down. I'm going to skip this, but because we have derived this before actually. This is actually, the first term is mu4, the fourth center moment, minus mu2 squared, minus 2 times 2 times mu4 minus 2 times mu2 squared over n. The last term over n squared, mu4 minus 3 times mu2 squared. Okay, those are the 3 terms. And previously, when we talk about asymptotics, we only keep this term, right? Because the other 2 terms will go down to 0. All right. With this, then let's take a look at the limit. Now, when we let this goes to let n go to infinity, we will be left with mu4 minus mu2 squared. And by our definition, this is our lambda f. No n anymore. N goes to infinity. Okay, so now when we do plug-in of the limit, what would it be? Lambda f n hat. When we do this limit plug-in, it should be to replace mu by m, right? Mu is based on f, m is based on sample. So m4 minus m2 squared. So this would be the 4th center sample moment. This is the square of the 2nd order sample moment, center sample moment. Okay, so I'm not going to write it down, so it's just a formula, but I think the concept is here. This is the plugin. Okay, now what do we do if we do Bootstrap? Then we're going to work on this and replace f by f n hat. Okay, we do Bootstrap. Okay, and I call that, we call it lambda n f n hat. Okay, so you see, when we do the plugin for f n hat, then everything here should be replaced by f, right? It should be very obvious. So I'm just going to write it, changing mu to f, mu to n. m4 minus m2 squared, first term, minus m4 minus 2 times m2 squared. Finally, n squared, m4 minus 3 times m2 squared. Okay. Okay, the question we want to ask is, which estimator is better? What's your answer, actually? Which estimator is better? Now we have seen enough asymptotics. Actually, they are largely the same. They have the same dominant term, right? They differ only in the term with order 1 over n and 1 over n squared. So therefore, we should say asymptotically, they are equivalent for those 2 estimators. Yeah, so this is it. So actually, if you also look at it, you can see that when I take the difference, let's see, when I take the difference between this and this, let me just write it. So lambda f n hat minus lambda n f. Okay, if I take the difference between this and this, I'm having just m4 minus m2 squared minus, okay, mu4 minus mu2 squared plus big O 1 over n. That's what I have. Yeah, this is 1 over n. And this is not OP because these 2 terms are fixed. But if I do lambda n f n hat, the bootstrap minus the performance, so it's the same thing. This is the same, but the last term is big OP 1 over n. That's it. So in terms of asymptotics, they are equivalent. So, okay, so this is one case. So that's why I say example 1, where it doesn't matter much which one you use, the classical estimator or the bootstrap estimator. But I want to give you a very interesting conclusion. This was a very famous result back in the 1980s by Peter Hall, who was a 1990s, who was a very famous theoretical statistician. So he studied bootstrap extensively, and he basically showed a very interesting result. So here, the limit of lambda and f would be depending on f, right? Because mu4 and mu2 are parameters of f. So in this case, he showed that basically doing classical plugin and bootstrap don't make much of a difference. But if we have this performance convergent to a limit that doesn't depend on f, so the limit just some constant, not depending on any parameters of f, then interestingly, we have advantages for bootstrap. So that's something very interesting. The bootstrap can do better than the classical plugin. And let's take a look. That's why we call example 2. So let's look at the bias. Okay, so again, for this parameter and this estimator, not examining the variance as the performance, but the bias. Let's say we are interested in this expectation under f of the estimator M2 minus the parameter mu2. Okay, and everybody knows that this estimator, as for estimating this, right, it's a biased estimator from our, introductory mathematical statistics. The reason it's biased, so because it's biased, we do n-1 as the unbiased version. This is like the specific case of the V statistics being biased, and so we go for the U statistic, and that will give me n-1. Okay, so coming back here, essentially we can show that the bias is actually mu2 over n. That's the bias. And if I let n go to infinity, what will happen? 0. Okay, because for mu2 finite. And this is my lambda f by definition. So now you can see the limit doesn't depend on f anymore. Okay, so in this case, if you do classical plugin estimator for this performance bias, of course, you would just go for 0. There's no better choice. So lambda f and hat should be just set to 0, okay? How about bootstrap? For bootstrap, lambda n f and hat, so this is the plugin. This is the bootstrap. For the bootstrap one, we do plugin. Then we should plug in this, right? So it should be m2 over n. Okay, so what is the m2 over n? Again, we know that by the asymptotics we described for m2 and mu2, we should be able to write m2 as mu2 plus big OP 1 over root n. We just use this result, divide by n. Okay, so what is this? If you look at it, you can see that it's equal to this thing, lambda n f, the parameter we are interested in estimating, or the performance we want to estimate, plus big OP 1 over n to the power 3 over 2. Okay, so now you see the interesting result comes in. If I compare this estimator with the performance, lambda f and hat minus lambda n f, 0 minus So it's minus mu 2m. It goes down to 0 at the order of 1 over n. While my bootstrap lambda n f and hat minus lambda n f, I already have it, is big OP 1 over n to the power 3 over 2. So you see, this goes down to 0 faster than this one does. And this shows the advantage of Bootstrap. So this is a very interesting result, right? A sort of counterintuitive. But again, I think the key is because when you do plugin, you are plugging the limit. And when there's the limit is a constant, you just take that limit constant as your plugin. So there's not much you can do. But when you do Bootstrap, you still work with this term. Okay, so I think that's all I want to say about Bootstrap. And I think this will conclude our last lecture. I want to give you more time to do your presentation to prepare for next Wednesday. So I hope everybody's getting ready for that. And also, if you haven't done so, please check your presentation order on CCLE so you can see what time you will present. But regardless of that, everybody should be there on Zoom to do the presentation. Okay, so before we conclude, do you have any questions about the Bootstrap or anything in general we have covered? So maybe I can ask a question for you guys. So what do you think is something you learned as new after this Bootstrap topic? So before you learned this, I think many of you have used Bootstrap before, right? In application. No comments? I think for me, you know, the Bootstrap version, when I first learned this, the version I learned was to do the Monte Carlo one. So that's where everybody talks about it, right? So you actually skip that two-step argument. But with this understanding, then you can see, yeah, the capital B is something, the larger the better, that's for sure. But still, it's not a magic, right? Even if the problem is not well posed for Bootstrap, like the boundary parameter. So in that case, no matter how large B is, it won't work. So hopefully, I think that's something everybody can take away. And also we can say that we use statistic, right? Anything, any parameter and its estimator can be, if the estimator can be formulated as a U statistic and the parameter must be some expectation function of F. When that's the case, then it's the comfort zone of Bootstrap. Okay. All right, so thank you all, and I'll see you next Wednesday on Zoom. I don't think so, yeah. So you will have more time to prepare for the I was debating actually. I don't know whether you guys want me to give another lecture about something. So if you want to, I can do it. I think something not covered in the notes is something, I think something important but not in the notes is the likelihood ratio statistic. So why it has a asymptotics. If very interesting, we can talk about that on Monday. What do you think, Chris? Okay, sure. Then let's do it on Monday. Yeah. Okay, yeah, sure. Okay, I'll see you on Monday then. Yeah.